So today we're going to be starting with the next spread, which is 4.4, and we're going to look at acid reactions. We're also going to look at this idea of comparing acids and bases. And you might have done a little bit about this last year as well, when you were in year 9. But today we're just going to look at it. And towards the end, I'm going to show you guys 3 examples of acid metal reactions. Okay, so the main idea being we need to understand the chemical equation. So just to do a quick recap, and again, some of this you might have learned last year. Acids are a group of chemicals with similar properties. Okay, and when we talk about acids, we can actually divide them into 2 types. We can talk about strong acids and we can talk about weak acids. How strong or how weak an acid is also dependent on its concentration, which basically means how many molecules of that acid are present in a specific solution. Okay, strong acids are more reactive and they convert into ions, or they ionize completely. Okay, ionize means that they basically lose the hydrogen ion that's attached to the compound there. Okay, so they convert into ions, so they ionize completely in water, and that's what makes them more strong. Now, common examples of strong acids that we've looked at are like hydrochloric acid, nitric acid, sulfuric acid, or sulfate. Okay, these are all examples of strong acids. These are the acids that also tend to be more corrosive. Okay, these are not safe for us to just be handling with our bare hands, whereas weaker acids are acids more related to the acids we find in food. Okay, they are safe. If you get a bit of lemon juice on your hand's not going to burn, for example. Okay, they're not as corrosive as the stronger acids are. And for that reason, we use weak acids, or we consume weak acids in food. For example, if you've ever had a salad with salad dressing and it's got vinegar in it, that's acetic acid. That is a type of weak acid. If you've ever had lemonade, that's citric acid, which is again a type of acid found in food. These acids are safe for us to eat because they're weak acids. And what weak acids mean is that they're less reactive with the environment that they're in, and that they only partially ionize or convert into ions in water. Okay, so that's basically the difference between strong acids and weak acids there. Okay, and this is just the chemical formula for acetic acid in vinegar. Okay, some other characteristics of acids is that they have a pH of less than 7. And we'll have a look at the pH table in the next slide. They tend to have a sour taste. Okay, if you've ever had lemon juice without adding like water to it, it's quite sour in taste. Okay, and the same thing can be said for vinegar as well. Turns litmus paper red. We're not too concerned with that point. The taste, again, we've talked about taste sour. Molecular compounds. Okay, so generally our acids tend to form molecular compounds there. So, for example, I can represent the formula of acetic acid in vinegar, or I can represent hydrochloric acid as a covalent diagram. Okay, covalent bonding occurs to lead to the formation of these compounds or these acids there. Okay, all acids ionize in water. Some acids ionize partially, they don't go the full way. Some acids do. Okay, depending on the extent to which the acid ionizes in water, that will really determine whether that acid is a strong acid or whether that acid is a weaker acid there. Okay, and ionizing in water is related to this concept that all acids donate a hydrogen ion. Okay, obviously when we talk about a hydrogen ion, we know every atom has the number of protons is equal to the number of electrons. In hydrogen, we've got 1 proton and 1 electron. So usually what happens is that acids will actually donate that hydrogen electron, or the electron, the negative one, to any substance that it's in, usually water. Okay, and we'll learn a memory tip to remember that acids are always the one donating or giving away the hydrogen ion. Okay, and bases are always accepting the hydrogen ion. Okay, and this is the kind of what we call as an acid-base reaction. Okay, and obviously acids contain hydrogen, and that's the reason that they're able to donate that hydrogen ion. Okay, so that's the basic idea there. Okay, let me just accept some people in. Okay, now in contrast to acids, we have bases. Now a base is if an acid is the one that kind of donates its hydrogen ion, where does it go? Where does the hydrogen ion that acid has donated go? It goes to the base. Okay, and this is why acids and bases tend to react with one another. Okay, they tend to interact and have kind of a connection there. Okay, because the hydrogen ion that's actually donated by that's actually donated by the acid actually is accepted by the base. Okay, now bases tend to have a bitter taste as compared to the sour taste of acids. Okay, bases tend to have a more bitter. So just remember B for base, B for bitter. Okay. They tend to turn litmus paper blue. Again, we're not too focused with the litmus paper for now. They tend to feel slippery. Okay, so if you've ever taken any product from your laundry, like dishwashing liquid or anything of those products, and if you've ever come into contact with that, you'll notice that your hands start to feel a bit slimy and slippery, and that's because most bases are slippery or slimy in nature. Okay, that's how their kind of texture is. They tend to have a pH of greater than 7. Okay, and this is the pH scale. You might have seen this in previous years in science. You can see that right in the middle, we've got neutral, our neutral scale, and then we've got acids to the left of that, and we've got bases to the right of that. Okay, so that kind of shows you where common everyday products or objects, or, in some cases with the acids, some foods lie on the pH scale. Now, bases that dissolve in water are called alkalis. Okay, if you've ever come across the word alkaline solution, that basically means a base that has dissolved in water. Okay, and like acids, like with the case of acids, we said some acids are strong and some acids are weak. We also have some bases that are more, we could say, reactive or more stronger than others. For example, if we look at our pH scale here, you can see that a base like baking soda or soap is kind of weaker compared to a base like bleach. Okay, and so for that reason, bleach might probably feel a lot more slippery or a lot more slimy in nature compared to baking soda. Okay, if we look at this pH scale here. So again, bases accept, or they tend to gain a hydrogen ion. So I'll give you guys a memory to remember this. Some bases, although bases tend to not be corrosive like acids are, some bases can actually burn the skin. So they can kind of have similar properties to acids there. Okay, only some. For example, sodium hydroxide is one of them, caustic soda. Caustic soda, you find that in a lot of your laundry products. Again, this is why on bleach, if you've ever looked into a bottle of bleach and you've looked at the label, it often says keep out of reach of children. Do not, if contact with the skin occurs, call this number, or, if accidentally swallowed, call this number, because obviously some of the bases can be more corrosive, particularly the stronger ones. Okay, so that's basically talking about bases. Okay, so Mylanta as well. This is calcium carbonate. That's also an example of a base. Okay, and so a lot of the time when, for example, you've eaten like really spicy food maybe, and there's a lot of acidity happening in your stomach. I don't know if you guys have heard of the condition called acid reflux. Okay, acid reflux is similar to heartburn. Okay, it's when you eat something that's too spicy and kind of all that spice or all that kind of acidity kind of just sits in your stomach and causes a lot of discomfort there. Usually when that happens, we take something called an antacid. Okay, an antacid is kind of like a tablet that is like anti-acid. So it tries to work to go against the acidity in your stomach to bring it back to kind of like a neutralized or neutral state there, where it's not uncomfortable and not causing you a lot of discomfort there. Okay, so remember, acids and bases are kind of opposite to each other, but then they also kind of counteract one another. Okay, so that's the basic idea. Okay, this is the memory tip I was talking about. So remember, bases accept, acids donate. Okay, so bases accept the hydrogen, the proton there, and acids tend to donate that. Okay, so that's the basic idea. And obviously when acids donate their proton, they only have one proton to begin with. So they basically just end up being an atom there. Okay, so that's the basic idea. And this is connected to the strength and the weakness of the acids and bases as well. Again, this is the pH scale, just a summary, just similar to what we've already gone through, but just a summary for you guys to understand the characteristics. Okay, so that's the basic idea there. Okay, when we're looking at neutralization reactions, like I said before, we have acid-base reactions where an acid and a base are mixed together. Okay, these are called acid-base reactions. When this happens, hydrogen ions from the acid combine with the hydroxide ions that are commonly found in bases to form water. Okay, and this is why when we, for example, have a reaction known as a neutralization reaction, the products of that neutralization reaction are always water plus a metal salt, always. This is like a formula, okay? And we're going to look at more of these on Monday when we look at the different types of metal and acid reactions, okay? But this is a common example of a neutralization reaction. So in the test or the SAC or the exam or whatever, if we were to give you, an equation where there's a clear acid, like hydrochloric acid or nitric acid or whatever it is, plus some hydroxide, so sodium hydroxide, lithium hydroxide, whatever metal hydroxide there is, okay? The products of that can always be predicted to be the name of the metal involved there, plus the salt that forms from the acid, okay? And we'll go through this a little bit more on Monday because there's a formula of how to do it, okay? It always follows that same formula there. So you got sodium, which is the name of the metal taken from the second part here, okay? And that obviously, hydrochloric acid is an acid which actually forms the metal salt known as chloride, okay? And you can kind of get a clue of why that is just by looking at the name. Chloric acid gives us chloride. So this acid forms a metal salt. That's where the metal salt comes from. And that metal salt is called chloride. So all I've done is gone sodium and then just put chloride there, okay? And water is always a constant. Water will always be one of the products in your neutralization reaction, okay? We're going to do a lot of examples of this on Monday, but just for you guys to have a basic idea of the formula of a neutralization reaction, this is what it looks like, okay? An acid could be any acid plus a base, which is usually a metal hydroxide, will always give us two products, which are water, that's our constant always, and a metal salt. So depending on your equation, your metal salt will be different. For example, if this was nitric acid, let me write that down. If this was something like nitric acid plus sodium hydroxide, okay, that would then extend this. That would then give us, if we look at this, so we've got sodium here and we've got nitric acid. So nitric acid forms a salt known as nitrate. Okay, so we go sodium, nitrate, and then our constant will always be water, remember? So then we write water. Okay, or water plus sodium nitrate. The order isn't too important. Okay, so that's the basic idea there. Okay, so that's just the formula we use for a neutralization reaction. And remember that when we see a neutralization reaction, or when we see even just the left-hand side of this equation, we can kind of predict what the products will be. Okay, and this is one of the benefits of classifying chemical equations, as we talked about last time. Okay, if we know that this is a neutralization reaction, even before you tell me what the products are, I can make a little estimation or a guess as to what the products will be. Okay, so it's really good for predicting the products of a chemical equation. So that's what a neutralization reaction is. In very simple terms, it's when you mix an acid and a base together, and basically you get two products that form out of that, which are water and a metal salt. Okay, that's the basic idea. Okay, whoops. You can see another example here. I didn't really refer to this, so I'll just quickly go through this one as well. Another example here, again, an acid, which in this case is hydrochloric acid, a base, which in this case is a metal hydroxide, in this case it's sodium hydroxide, give us water, H2O, plus sodium chloride, which is the salt that's formed. Okay, so you can see it's always the same formula. Okay, if you put these two together, regardless of what they are, they'll always give you water and a metal salt. Okay, that's the formula. Okay. All right, guys. So like I said, on Monday, we're going to go through some examples of common acid reactions. We have a worksheet for that. There are three main types of acid and metal reactions. Okay, these are the three main types we learn about. So the first one is basically what reaction occurs when an acid and a metal combine together. The second type of reaction is what happens when an acid and a metal oxide, for example, sodium oxide or magnesium oxide form together, and what kind of chemical equation we see when an acid and a metal carbonate combine together. So for example, when hydrochloric acid and calcium carbonate form together, what kind of a reaction or equation can we see there? So you can see for each type of equation we have here, we've got a specific kind of constant products that are forming as a result of that equation there, okay? So whenever an acid and a metal form together or combine together in a reaction, we've got two main products that form. That is a metal salt and hydrogen gas, or just hydrogen, okay? Now, this picture here is a picture of a statue that's actually been affected by acid rain, okay? Acid rain is basically a type of rain that is quite acidic in nature, obviously. And so what it does is that when it hits or when it pours down on objects that are made of metal or objects that are prone to corrosion, that acid rain actually starts to corrode the material that it falls on, okay? So we can see here that, you know, this is the formula that kind of represents acid rain, the worded equation, we can say, okay, because we're just using words here. We're not putting any chemical symbols here. So sulfuric acid, which is also known as hydrogen sulfate, plus zinc actually combine together to give us, what are we expecting? A salt and hydrogen. So hydrogen's here, that's always the constant, and a metal salt. So because we had zinc as the main metal that was involved and sulfuric acid as the acid, sulfuric acid will always produce the salt known as sulfate. Okay, so that's why we just combine zinc and the sulfate together to give us the metal salt known as zinc sulfate. So zinc sulfate plus hydrogen. Okay, that's just the formula. That's the template. That's the template we're going off. Okay, and that is the two products we can expect to see. If you were to change that, or if you were to put that into a chemical equation, that's where we're using our chemical symbols. Okay, so hydrogen sulfate or sulfuric acid that's the formula. Zinc we know is just Zn, and then zinc sulfate is like that, and hydrogen obviously exists as a diatomic molecule, which is why we've got the two there. Okay, that's hydrogen gas. So it's H2. So that's the first type of equation that we look at when we talk about common acid reactions. The second type of common acid reaction that we have is when an acid and a metal oxide combine together. So in this case, the products that we can expect to see in our template for the second type of reaction are metal salt again, and this time water. So no more hydrogen gas, this time we're talking about water. Okay, so we can see nitric acid is the acid here. Magnesium oxide, magnesium is a metal and oxide is an oxide. Okay, so magnesium oxide is our metal oxide. Okay, and they give us the products of magnesium nitrate. Remember we said nitric acid always forms the salt known as nitrate. Okay, and the name of the metal in the here is magnesium. Okay, so magnesium, and then just combine that with the salt form, which is nitrate, plus water is always a constant. Okay, in each of these reactions, guys, I'm going to talk about this when we finish these three equations. You have a constant. Constant means that thing will always be present regardless of what else changes. Okay, and we'll talk about the three constants. Okay, now that is the reaction. Okay, nitric acid plus magnesium oxide gives us magnesium nitrate, which is the metal salt, plus water. Okay, if we were to write that into a chemical equation, that's what it would look like. And you can see this one has been balanced as well. Okay, so that's just the chemical formula. We'll do more of these chemical formulas on Monday, but I just want to get your head around the basic template that we use first. And so when we do it on Monday, it's just a matter of we just applying what we've learned today. Okay, acid and metal carbonates. Okay, this is the third type of acid reaction, acid metal reaction that we see. Okay, so acid and a metal carbonate. For example, nitric acid again, plus calcium carbonate. Remember, a metal carbonate is just a metal in front of carbonate, okay? Some kind of compound that's basically formed as a result of a metal combining with carbonate there. Again, carbonate's just a compound made of, you know, one carbon atom and 3 oxygen atoms there. Okay, so calcium carbonate gives us, and what are we expecting to see? We're expecting to see a metal salt, there should be a comma there, a metal salt, water, and carbon dioxide. Those are our three expected products that we can predict. Okay, if we look at our formula here, we can see that we've got water, we've got carbon dioxide. Okay, and the metal salt, we have to look at what metal is involved. In this case, it's calcium. The acid that's involved is nitric acid, which we know forms the salt known as nitrate. Okay, so then we've got calcium nitrate. That's our metal salt. Okay, I say metal salt rather than just saying salt because it's not just a salt, but it's a salt that's got a metal in front of it, okay? Whether it's calcium, lithium, magnesium, whatever metal it is, it's got the name of a metal in front of it, okay? So here we can see, guys, can anyone tell me in this third type of equation here, what do you think are the two constants that will always be, the two constant substances that will always be present, regardless of what equation we have for the third type here? So if our products are calcium nitrate, water, and carbon dioxide, what do you think are the two products that will always stay the same, regardless of what equation we have, or that will always stay constant according to our rule? There's one thing in there that will change. So out of this, and this, there's one thing that will always change, but two things that will always stay constant or the same. Anyone want to take a guess? Excellent, good work. So water and carbon dioxide stay the same. Good girl. So basically that means water and carbon dioxide stay exactly the same, okay, in every equation. Now, when we do this on Monday, you'll realize that it's actually a lot easier to do this when we actually start doing a bunch of equations compared to just looking at a few examples here, okay? Now, speaking of constant, I just want to quickly go over and highlight the constants in each reaction. So in the first type of metal, acid and metal reaction, we had hydrogen as the constant. Zinc, the metal salt can always change depending on the metal. In this, we had zinc, but if the metal here was magnesium, we wouldn't have zinc sulfate anymore. It would become magnesium sulfate. Okay, so depending on the metal that we have, this part can change, but the hydrogen gas is always constant. That will always be the same. Okay, in the second type of reaction that we have, again, water is the constant. We'll always have H2O in our chemical equation when an acid and metal oxide combine, but the metal salt can change. Okay, so for example, if I have sodium here instead of magnesium oxide, this will obviously, the product will obviously no longer be magnesium nitrate, it's going to be sodium nitrate. Okay, so that's just showing you that the metal salt is always prone to change, but that water will always be the same. In the third type of metal and acid reaction we looked at, basically, you know, the same thing. Water and carbon dioxide are constant. Those don't change. But depending on the metal that we have, the metal salt that's formed, which is this part here that I'm drawing a box around, this can change. Okay, if I had, for example, magnesium here instead of calcium, this would become magnesium nitrate. Okay, or this would become lithium nitrate. So depending on the metal that you have, your metal salt will always change, but water and carbon dioxide will remain. They are the constants of that reaction there. Okay, and we can see them here. They are always the constants. Okay, this is prone to change depending on what metal we have highlighted in our equation. Prone to change, but these are constants. Okay, so all of these in pink, these will stay the same regardless of what equation we have. This will stay the same regardless of what equation we have. And hydrogen gas here, this will also stay the same regardless of what equation we have. Okay, guys, so those are the three types of metal acid reactions, okay? When metals and acids come together, the kind of reactions that we see. So it's really important to understand how each one of these is different, as well as the things that will stay constant and the things that will change, okay? For most of these, it's the metal salt that is always prone to change. The rest of the products remain constant there. Okay, now you might be a little bit confused as to, okay, where did she get sulfate from when she said sulfuric acid? Where did she get nitrate from? How does she know that nitrate is the salt formed from nitric acid? They're just the basic, again, rules or the basic templates. Okay, for example, if we talk about the different types of, you know, salts, sulfuric acid is always said to produce the salt known as sulfate. Okay, nitric acid is always expected to produce the salt known as nitrate. Okay, these are just basically things that will these are just acids that will always or consistently produce that specific type of salt. Okay, so before we start doing the equations on Monday, we'll jot all of these down in front of us on the slide, and then we can just keep referring back to it. Okay, so what I want you guys to do for the rest of the lesson, and I think, wait, let me just check that that was the last slide. Oh, sorry, one more slide to go before I finish off. Okay, so I already talked about in the beginning that depending on the acid and whether the acid is a weak acid or strong acid, we can actually make a judgment of the concentration of that acid as well. Okay, so for example, the concentration of an acid is how many molecules of that acid or base are present in a liter of solution. Okay, some acids we said, for example, hydrochloric acid is an example of a strong acid. Okay, a strong acid means that it's very reactive. It readily reacts with anything that's in its path. Okay, that's the basic idea. It readily reacts with anything that's in its path, or that it comes into contact with, in other words. Okay, so this is why in the lab, generally we don't store acids in metal jars or in metal containers. Okay, the reason for that is that metals, as we looked at the 3 types of metal reactions, metals are very reactive and can react readily with acids and vice versa. Okay, for that reason, if we were to put a hydrochloric acid quantity of hydrochloric acid in a metal container, the next day we might come to find that that metal container has literally corroded, or that there's hydrochloric acid seeping out of that metal container. Okay, for that reason, we generally tend to store a lot of our common acids, like hydrochloric acid, in glass jars or glass bottles there. Okay. Strong acids and strong bases tend to be dangerous to handle, even at very, very, very low concentration. So we don't generally use a lot of hydrochloric acid in the lab, okay, just because it's very dangerous and it's very corrosive. Even if you were to get like a tiny sliver of hydrochloric acid in contact with your skin, it could be very, very harmful. Okay, and we've already talked about this before, but basically the strength of the acid is basically dependent on how readily or quickly it donates the hydrogen ion to a base. So again, this is kind of connected to how easily electrons or protons are lost. Okay, so if you lose that proton very quickly, okay, that hydrogen positive ion, or that cation, the proton, if you lose that very quickly, then that will basically mean that the acid is stronger. If you accept the hydrogen ion from the acid very quickly, that means the base will be stronger. Okay, that's the basic rule there. The higher the number, the higher the concentration. Sometimes we've got hydrochloric acid and it might say something like 3.0. Okay, the higher that number is, the more concentrated it is. If it's lower, like 1.0, for example, usually this is labeled on the bottle. If it's like 1.0, that means it's got a lower concentration. Okay, so that's the basic idea. Okay, so that's basically talking about the concentration between acids and bases there. Okay, so I think, okay, and this is just a summary of the entire thing that we just went through. Okay, so today we learned about neutralization reactions. Okay, we also learned about the 3 types of metal acid reactions, and we also learned about the difference between concentrated acids and concentrated strong acids, as well as weak acids, and also strong bases versus weak bases there. Okay, so always remember, you can use that memory tip to remember which one accepts and which one donates. So the acids always donate the hydrogen proton, whereas the bases always accept. Okay, and depending on how quickly they accept the proton or how quickly they donate the proton, that will determine the strength of that respective acid or that respective base there. Okay, guys, so what I want you to do for the rest of the lesson is, well, I'll just stop the recording here to begin with.